Yes. One thing, so perhaps I could actually talk a bit about what I didn't talk about yesterday, is that when you hear or you plan to attend the natural language processing lectures or courses, often you have an expectation that you're going to, in fact, hear about language, right? So, what kind of languages are we going to build a system for? What are the characteristics of different languages? And then what are the problems in natural language processing that need some knowledge about language in order to be solved, and on and on. But I'm sure, all of you have somehow noticed that during my lectures, there was almost absolutely no mention of any specific language. Not to mention even examples that were written in any exotic languages. There was one example written in Korean for the tokenization, but even then, Korean is not really a rare language at all. It's actually spoken by more than about 75 million people in the world. So it's actually one of the most spoken languages in the world. So the reason why I always take that route in order to teach natural language as processing to my students and then the people all over the world is because there are two sides to any kind of problem that we try to solve with the machine learning or more broadly AI techniques. One is the side of the domain expertise. So if I want to build a natural language processing system or machine translation system or any kind of natural language relevant systems, there is a huge amount of domain expertise that's necessary. That is about language. And then that domain expertise often comes from the field of linguistics, psychology, and so on. But at the same time, there's yet the other side of the solving problem is AI or the machine learning techniques. And then each of these two sides is just too broad or wide for me to be able to cover in entirety over 3 hours. Even a full semester would not be enough. Right? So, and then what do I know about language? This is what I always say to people who ask me about language because they think that I do work on the language related stuff. So I focus on the machine learning. And then what I hope to convey, because I was looking at the schedule of the summer school, is that all these techniques that you have learned are applicable to broad set of domains. All you will need is to be able to find the good collaborators or the partners who have a strong domain expertise and then listen to them and then trying to make sure that the system you're going to build are in fact going to solve the real problems in the domain. And then, in fact, the order was a bit flipped, but all of you have heard from Katharina about how to build such a system for a very particular, let's say, linguistics related problem, such as morphology and so on. So in a sense, the recap of what I taught yesterday is that I taught you everything that has nothing to do with language in natural language processing. And then hopefully with your knowledge of your own target language and your collaborators who are more, who have better expertise in language, you'll be able to build a natural language system, a processing system that in fact uses all these state-of-the-art technologies from the AI. And then what you realize is that in fact, all the things that you have learned from other lectures throughout the summer school are applicable. And then many of my latest research are focused on how to build or come up with a new machine learning algorithm with the application to natural language processing in the mind. So in that sense, it was more of a machine learning lecture than natural language processing lecture. So my apologies if you had a different type of expectation, but I'm sure this has been better, not only because of the choice of the content, but because I'm so much more comfortable talking about machine learning than the language as on its own.
It was very comprehensive in any case, so there is a lot of takeaways. But if we start with the questions themselves, well, so you were saying that so throughout the lectures we have learned a lot of general methods that can be applied to specific problems. But what if we look at NLP problems or NLP ideas, which are useful to other communities working on sequential data, but that are not well known yet?
Right. So that's an interesting thing. So often when I talk to many people who are not familiar with how machine learning works or the AI works, or who are just getting into this field, they have a very interesting kind of view where they think that, oh, here's a group of people who are just churning out those new algorithms without knowing how those algorithms are going to be used, and then writing down the theory behind all these algorithms. And then there's another group of people who are going to just receive all those stream of new algorithms and then trying to use them for their problem. But it turned out that's actually not the case. What in fact happens in this machine learning, AI, and this kind of engineering domain is that it's always a two-way street. We cannot come up with an algorithm without knowing what kind of problems there are out there. And then also the problem solvers cannot use the algorithms blindly without knowing exactly what is going on behind those algorithms, and then what are the theoretical foundation behind them. So in a sense, it's often a very complicated, let's say, conversation between the theory researchers, algorithm developers, and then various domain experts. So in my case, that has been natural language processing and machine learning in particular. So interesting thing is that until I started my postdoc with Yasha Benjo in Montreal, I really had absolutely no idea anything about no idea about natural language processing or natural language in general. Only when I joined University of Montreal as a postdoc, I started working on, okay, so can I actually use the knowledge that I have about the generative neural network for solving the problem in natural language processing, in particular machine translation. And then what I actually have done back then was to learn a lot from learning about the problem itself. It was a sequential data with a variable length input, variable length output, and then the space was really large, and that there was issue with the inference, and then not and learning, and all those things that I didn't even imagine I would worry about. And then a lot of the things that we learned back then have been now absorbed into all these machine learning algorithms. So of course, there are always many different motivations, and then you had the inspirations behind a single algorithm. But for instance, residual networks. All residual network ResNet comes from the fact that there is a difficulty in training a recurrent neural net on a very long sequence. And then that difficulty is vanishing gradient that we learned about yesterday. And then in order to avoid that, we talked about how to introduce all these shortcuts. And then residual connections in ResNet are all those shortcuts. So in a sense that if we did not have recurrent neural net research in 90s, and then if we did not have, if we hadn't had people working on trying to use recurrent neural net for very long sequences, we may not even have had known that this kind of problem existed. So in a sense, it's always a two-way street. And there are a lot of the techniques that we have developed in order to cope with the natural language, especially long sequences and the hierarchical structure, like the unknown hierarchical structures, have in fact been applied to various other domains. For instance, if you are familiar with the computer vision, and then I'm pretty sure there was at least one lecture in the summer school that mentioned this technique called pixel CNN or the pixel RNN. The idea of using an autoregressive model, using a recurrent net or the convolutional network for modeling images at the pixel level is exactly what we learned how to do with the text. In fact, the person who proposed pixel CNN and pixel RNN, and well, one of them, Niall Kalkbrenner, was one of the very first people who applied the neural net to the machine translation problem in 2013. So in a sense, that idea is already there. And then that idea flowed from natural language processing via deep learning to computer vision. And then the attention mechanism that I spent quite a bit of time yesterday, that one also was invented or derived to solve the problem of the long sentences in machine translation. But then now you may have noticed, but the attention is really used everywhere. That goes from the particle physics, computer vision, to any place where there is some kind of graph structures. And then when you use a graph neural network, one of the main choices that you need to make is whether to use attention or not. So yes, so it's all kind of all interconnected. It's never a kind of, let's say, staged process that we have in this research of AI or the development of AI. It's more like a very complicated system with a feedback loop.
If my native language is not part of a major language and there are not many resources, which suggestion do you have so I can do research on NLP for my language?
Yeah, so indeed. So excuse me. If I could say one thing that really sets natural language apart from, let's say, computer vision or whatnot, is that it's it's heavily skewed. The data that we get is heavily skewed, and then the actual use of language is also heavily skewed. So what do I mean by the use is skewed? Is that like when you look at the word frequency or the phrase frequency and so on, they all follow so-called Zipf's law. So it has a very heavy tail. We always find some new combination of the words or the new combination of letters that no one has used or only a very few people used before, but somehow we can all understand because of the compositional nature of language. So that makes it really difficult to build a complicated statistical system that rely heavily on observing the phenomena from the data. Because in the data, there are so many phenomena that just occur very rarely on themselves. So then what is the right way to build a statistical system to capture that? And at the same time, we have skewness in data collection or the data that we see in terms of natural language. So the largest resource that we can gather our data from in terms of natural language is the internet. Internet is filled up with the text. Somehow everyone is writing something there. Now, the unfortunate thing is that due to the issue of the digital divide or the information inequality, the proportion of the languages used on the internet does not reflect the proportion of the language that are used in reality. So for instance, you go to Wikipedia, you check the Wikipedia in Finnish, the language in Finland, there are tons of documents. You can get a lot of resources on Finnish as a language if you go onto the internet. But in total, there are about 6 million people in the whole world who speak Finnish. Now, on the other hand, let's think about, I don't know, Indonesia, Malaysia, a lot of those Southeast Asian countries. The population there is simply orders of magnitude larger than the population of the Finnish-speaking people in the world. But if you're trying to look at the resources or trying to locate the resources on the internet that you can easily access, it's going to be orders of magnitude smaller than the resources in Finnish. So it does make a huge barrier to build natural language processing system for all the languages in the world. According to some estimates, there are more than 7,000 living languages at the moment. So it makes it difficult. So how do we actually overcome that? There are a number of directions that people have been taking. One is to indeed to create the resources that are going to be more, let's say, accessible, and then cover much broader set of languages. So you can go to some of the initiatives that focuses on languages in Africa, that focuses on, let's say, endangered languages and so on. Still, but that one is quite difficult because a lot of languages often don't have the written forms. And then there are just not many people who speak those languages left to spend their time collecting all this data or the creating the resources. And then the second direction that I think may be more promising is to build a system that can learn to transfer knowledge from one language to another. Because there are so many languages, and then we know that most of those languages are complete in a sense that whatever you say in one language, you can say the very same thing without losing any meaning in another language. What that means is that by looking at many different languages, we may be able to extract the underlying regularities behind the languages themselves, and then be able to rapidly transfer our knowledge obtained from a high resource languages into low resource language with a very small amount of the resource from the target language. And then that's where all this multilingual training, multitask training, and then unsupervised translation techniques come in. So you definitely need to look at the multilingual techniques that have received a huge amount of interest recently. So we didn't have time to talk about it in my lectures, but in Katharina's lectures, there was huge amount of emphasis on pre-training. And then you can think about pre-training a language model with all the languages in the world that you could get resources on, resources for. And then now will this kind of pre-training allow this language model to be able to transfer knowledges across different languages and thereby helping you build a better low resource language processing system? Big question, but I think that's a promising direction. There are a few other directions, but I don't think those are that important to talk about. I think we can move on to the next question.
And if I want to start doing research in NLP, which background knowledge, which prerequisites do I need?
Yeah, well, it depends on what kind of background you already have, of course. But, generally, well, as I said at the very beginning, right? So in order to recap what I didn't talk about yesterday, you want to have both the background necessary to develop an algorithm and also a background necessary to know how to apply that algorithm to a specific problem in natural language processing. So what that means is that, of course, you need to have strong background in mathematics, computer science, and then maybe like this a bit of interest in the physics and all the adjacent fields will definitely help, because that's going to help you build a theoretically solid algorithms. Now, at the same time, if you're interested in the natural language processing, you obviously want to know more about language than other people. But again, it's a large field that has multiple aspects, and then it's impossible for anyone to cover all those aspects. So it's up to you to decide, given the finite amount of resources that is time and effort, now which aspects of this large field of natural language processing you want to focus. And then once the focus is decided, you can think about what are the foundational knowledge you need to have in order to go further into that direction. And then that's how you're going to be able to make up a list of things. But the thing is that, but generally saying, you never know, right? Because we are now going forward. And then when you start doing research, you actually start working on things that no one in the world knows. And then, of course, in that kind of context, how would anybody be able to tell you, including myself, what are the prerequisite knowledge in order to get this new knowledge that no human in this world in the history has ever known? So it's really difficult to tell what is the prerequisite, but whatever you find interesting, I would say that thereby is.
And do you think that we are reaching the limits of deep learning as a set of techniques for NLP?
Well, it's difficult to tell what it means to reach the limit of a set of algorithms. Let me put it in this way. So of course, the language is a very complicated thing. It seems like a lot of problems can be solved very nicely these days, but that probably means that a lot of the benchmark problems that we have been using are just too simple. We probably need to just go further, and then we're going to very easily run into the obstacles that cannot be solved by any of the existing techniques. That's for sure. But then you start, in order to answer this question in more detail, I need to talk about what is this deep learning, or what are these deep neural networks, or the algorithms that we've been building. And one kind of a bit simplistic way to characterize this is a way to build a function approximator. That is, if we know that there exists some underlying function that generated a set of observations that we have access to, right? So the underlying function we don't have access to, but the data we have access to, then how well can we recover that underlying function up to let's say some transformation, right? So within the function, we don't really care what happens. However, in terms of being able to generate the same kind of data, how well can we recover that? And thinking about that, in fact, training these deep neural networks or the artificial neural networks is one of the only ways we know how to do that scalably. So at scale, both in terms of the dimensionality of the input and output, but also in terms of the number of the observations that we can use. So we use stochastic gradient descent, we use the backpropagation to compute the gradient. These two are like major ingredients that allow us to uncover those complicated functions underlying this high dimensional many observations that we get. It's not easy for me to imagine what other techniques there may be in the future that could replace deep neural net in this regard. And then if there's none, then what that means is that the deep neural net is here to stay, just because whatever the new paradigm we're going to come up with in terms of learning, AI, or natural language processing, that paradigm will have to rely on the existence or availability of good function approximator. And then that is going to be good time.
And predicting long sequences has been a perennial problem in NLP, but the attention mechanism is relatively new. How did people work with long sequences in the past?
Yeah, attention mechanism is relatively new, but it's already like 2014 that we worked on it. So it's been like 6 years. So I would say like at the pace of the advances in the field or the progress in the field, I would say it's a pretty old technique already. But yeah, so of course, to start with, attention is not necessarily the best way forward when you try to process a long sequence due to the computational complexity. Because every time we want to do something, we need to look at all the entire history, and then we need to compare what we have at the moment against the every possible time in the history, and then that leads to the quadratic complexity, right? So it's going to be the length times length eventually. Now, because of that, people have been looking into those sparse attention in order to ensure that the number of past steps that we look into or the run the attention over is going to be constant rather than the linear with respect to the length of the actual sequence. But that's still an active area of research. So, okay, so the attention is not necessarily best for long sequence, especially when it's really, really long due to the computational issues. However, let's say it still helps with the long sequence because we don't have to compress the entire sequence into a single vector. So that makes sense. What did we do before that, right? There have been a lot of different ways to go. So one way is what we learned about, that is that the people have been imposing the Markovian assumption, is that we only look at a fixed window into the history in order to capture all those dependencies without having to process the entire sequence. That's clearly suboptimal. Like we learned about the reason why it's suboptimal. And then some other approach has been to do the actual compression. So you could think about doing the compression at a various rate or the level. So it's going to be more of the hierarchical compression. So we're going to look at the past steps within some small window for every step. But beyond that, we're going to, let's say, look at the chunks at a time. So we can compress these chunks into a vector and then make it into a shorter sequence. And then if you think that that sequence of chunks is still too long, then we can also apply the same idea of compression on top of it. And then you end up with the hierarchical recurrent neural network that was, like the pioneered earlier in early 90s by, let's say, Jürgen Schumituber as well as Joshua Bengio. But that one is also quite difficult because you need to make so many arbitrary decisions. What is the right number of the hierarchies that we need to consider? What is the kind of, let's say, size of the chunks at each level that's going to be optimal? And can we in fact train all these things all together? That's not even clear, in fact, whether that's possible. So in a sense that the attention is a very natural next step that people have been looking into. That is, we need some way to compress them without losing too much information, and then building a hierarchy is a good idea with a different rate of update. Now, attention allows us to make that rate of update softer, and learnable. So in a sense, this answer is a bit weird, but we've always been using this mechanism of attention throughout the entire history of deep learning for sequence or the neural network sequence, except that the mechanism by which that attention pattern was created was often fixed or manually designed rather than learned. So the only thing that changed recently is that we know how to learn the pattern of attention automatically.
And in NLP, we see a lot around attention mechanism and also transformers. But are there other architectures that you see as up and coming?
Uh, no, I mean, like, it's difficult to do that. I mean, I've never been big on coming up with a good architecture myself, so it's difficult to tell. But I guess the sparse computation is going to be important. And then I don't know what is going to be the right network architecture to enable us to have sparse computation. And sparse computation is really interesting from many different perspectives. But in the case of the sequence processing, as we just talked about, sparse computation is a very natural way to learn to compress and ignore irrelevant. So I think the network architecture that's going to allow us to build in some kind of sparse computation is going to be important. So for instance, there was a paper from University of Montreal. I think the Goya et al. Had a, a nice idea of introducing the sparse computation in a recurrent neural net, and they called it recurrent independent mechanism. So that looks like a very promising direction. Although the network kind of had a lot of moving parts and a lot of ad hoc decisions that I wasn't really able to follow very carefully and then be convinced why those are unnecessary. But the idea of having a sparse computation seems to be very important and then for sequence processing, and then sequence processing is one of the fundamental, let's say, building blocks behind the natural language processing. So yeah, only thing I can say is that is some kind of sparse computation.
Can you please share with us some anecdotes about the gated recurrent unit? What was intuition, how they came up with, and so on?
Right. So the yeah, it was an interesting time. So I moved to University of Montreal as a postdoc in 2013 summer, and then I started working on machine translation because Yashua Bengio, my mentor back then, gave me four options for my research topic when I just arrived in Montreal. And then one of them was machine translation. I decided to pick machine translation because I had no idea what machine translation was. And I didn't know Yashua had much idea about what machine translation was either. So I was like, okay, that sounds like an interesting thing. And then I decided to work on machine translation. And first thing I did was to be as naive as possible. Let's say I need to solve this problem of machine translation without knowing anything about machine translation or what others have done. What what would I do? So naturally, because I was still a neural net kind of researcher, naturally my idea kind of went to the recurrent neural network. And then I thought we should have an encoding recurrent neural net, decoding recurrent neural net. Encoding recurrent neural net is going to read the source sentence, make it into a one vector, and then the vector is going to be passed on to the decoding recurrent neural net that's going to generate a translation. So I coded it up from scratch using Theano. And then I gotta say, these days, PyTorch, awesome, right? Very easy to use and everything. Back then, Theano was that very easy to use tool, but it wasn't that easy to use. And then that was almost the first time I used Theano like seriously. So it took me many months to figure out what is the right way to implement it, and then what is the efficient way to implement it. Thanks to the help from Razvan Pascanu and then others who were back then in Montreal, who are now in DeepMind. And then, so I implemented everything. Then I started training this model, and then I just could not train it well. I'm like the loss function was just not going down, or loss function would go down and then suddenly blows up, or all the parameters were just becoming not a number immediately. So it was a pretty frustrating, like half a year to almost a year trying to figure out what is going wrong. I was talking with Razvan Pascanu, who wrote a paper back then in 2013 about the gradient clipping for avoiding the exploding gradient. And then hinted at some of the underlying reasons why vanishing gradient happened. And then the unfortunate thing, or that was my laziness, is that I wasn't aware too much of the LSTM myself. So I was essentially at the stage of the early 90s. So right before Hawkrider came up with the idea of the LSTM, and then I was struggling there. And what I actually talked, how I described gated recurrent unit yesterday was in fact almost precisely how I came up with the gated recurrent unit, in a sense that the one thing that inspired me was there was a paper in 2012 from Yasha Benjio's lab by I think there was a Nicolas Blanchet. He wrote a paper showing that it's sometimes it's much easier to train a recurrent neural net if there is a leaky integration. That is, if you always add a bit of the previous hidden state to the next hidden state with some fixed coefficient. So that one indicated, okay, there has to be something. So we need to somehow pass the previous hidden state to the next hidden state without touching it too much. And then from there, one thing that was natural was that, okay, but if there is a fixed coefficients, can we just turn that fixed coefficients into a adaptive coefficients that's going to be computed automatically? And then one thing led to another. From there on, it was very natural to come up with a gated recurrent unit. And then thanks to Theano, implementation was very, very easy, because by then, I was completely familiar with Theano internal and everything. And then I trained the model with the new unit, and then voila, the loss function was just going down so smoothly. So that's how I came up with the gated recurrent units. And then of course all these connections came to me in whole only looking back. Like I got this model finally working, and then I started writing paper, and then I had to explain this unit. And then one thing that you do a lot when you write a paper is doing a lot of literature review. So as I was writing, I continued literature review, and I went all the way back to Seth Hochreiter's paper, and then I looked at all those previous paper from Yasha Benjio's lab and so on. And then that's when everything kind of, let's say, clicked. So all those things I read before just here and there, but without making the connection. But as I developed this gated recurrent unit, things kind of came together without me realizing. But once things started to work, I started to look back, and I was like, okay, all these ideas in fact click with each other, and you end up with a gated recurrent units or LSTM or any kind of network with the adaptive shortcut connection. And one of them was a highway network from the Jürgen Schumpeter's group done by the Rupesh Srivastava. And then there, he actually used this idea of the adaptive shortcut connection, just like ResNet, to the feed-forward network. And then he was able to train a feed-forward network with 100 layers in 2015, and which was back then like super, super deep. So yeah, that was the story, yes.
It's very interesting. But talking about RNNs, some studies show that a simple CNN properly trained can have similar or superior results to LSTMs on sequence data, and they are much easier to train. And on top, we have now transformers, which is a much more complex architecture. So where do you see now the need for RNNs? Where is the space for RNNs these days?
Yeah, that's an interesting question. So comparison between convolutional nets and recurrent nets is actually nonsensical, in a sense that let's say I can always create a problem myself that requires capturing the dependencies, long-term dependencies that go beyond the receptive field side of a convolutional network. You can always artificially create it. And in that case, convolutional network will just fail by construction, because convolutional neural network has always a fixed the receptive field side. So so I don't think it makes sense to actually compare them. So, or if you want to compare convolutional network and recurrent network, then you need to give them much better context. So for instance, okay, given this problem, is convolutional neural net enough to solve this sequence modeling problem? So then in that case, you could say that, oh yeah, maybe it's enough because you get a higher accuracy or comparable accuracy. So, and then that probably says more about the problem itself than the convolutional networks nor the recurrent networks. Now, of course, transformer is slightly different. Transformer is different in the sense that it can capture dependencies that span arbitrarily long, let's say, span, right? It's a long time lag. But of course, again, the comparing the recurrent neural net and transformer is also a bit nonsensical if you think about an extreme case of the infinitely long sequence or the stream of sequence, because you cannot really attend to every possible infinitely many past time frame. At some point, you need to come up with a way to somehow summarize what has been seen. And then now, what is the right way to summarize it? I think there is a recent paper from Facebook AI Research Paris that says that, yeah, we can use the idea of the memory network and then store the summary vectors in the memory, and then replace that, replace the infinitely long history with that kind of memory stuff, for instance. However, like that's essentially kind of making into a hybrid between recurrent net and transformers, which I think is a perfectly fine way to go. Now, back to recurrent nets alone. So is there any case where the recurrent nets are going to be very useful and then, powerful still compared to transformers or the convolutional networks? First thing is that the human brains are recurrent nets, right? We cannot store the copies of our brain activations that easily and then do the attention. So we do have a very nice example of a recurrent neural net that is very, very powerful. That's a human brain. But what that in fact implies is that you start thinking about this scenario of the lifelong learning, and then the necessity of updating all these parameters all together as you process the sequence. So it's an infinite long, never-ending sequence or the never-ending episode. And then it's not Markov decision process, so you actually do want to look at all the previous time steps because you don't know what you are not observing in the current state, current observation, current time. So you want to have a recurrent network, and then you cannot assume any, let's say, fixed window that you can look back into, and then you need to update on the fly. Then that's where the recurrent net is going to be one of the only alternatives we can imagine. Now there's one kind of the same difficulty is that what is the right way to update our recurrent net parameters on the fly? There was a lecture at the summer school about the online learning, so a lot of, let's say, techniques from there can be used here as well. And also there is a set family of learning algorithms for recurrent neural net called the real-time recurrent learning that I didn't have any time to go into, but an algorithm from that family allows you to in fact update the recurrent neural net on the fly. But they are often very expensive, so that's the reason why not a lot of people are using it. However, in my opinion, combination of a tractable approximate online learning algorithm with a recurrent neural net is going to be one of the solutions to online, well, not online, but the lifelong learning system that can adapt on the fly. And then that's going to be like the human brain at the end of the day.
And Jan LeCun advocates for energy-based models. Where do you see here intersections that complement RNNs?
So yeah, the recurrent nets are parameterization. So I want to compute some conditional probabilities of some observation. I want to compute some conditional distribution given some input. Then in order to compute the sufficient statistics of those distributions, we can use recurrent neural network, convolutional network, transformers, or whatnot. Now, energy-based model or the energy-based learning it has a much more focus on the learning side. Say I want to solve this problem where given an input, there are multiple possible answers, multiple possible good answers. Then what is the right way to train this parameterization or the neural network to capture all those different answers? And then energy-based learning is telling you that you're trying to decrease the energy of the one observed answer out of many possible answers. And then you try to increase the energy computed by this neural net of what this neural net thinks should be answers. So that's like the basic principle. And then if you think about it, then this energy-based learning can be used with the recurrent networks, convolutional networks, transformers, whatnot. So we need to, like the important thing to remember is that the machine learning is each of these models is not a monolith. It's more like what is the set of decisions or the choices we have made in terms of learning algorithm, inference algorithm, and then the parameterization. So for instance, yesterday, the autoregressive language modeling, our choice, the parameterization was that we're going to use a recurrent neural network to compute the conditional distribution, where this conditional distribution computes the distribution over the all possible tokens, given all the previous tokens. And then we decided to use the greedy decoding or the beam search as inference algorithm after training is done. And for learning, we decided to use a maximum likelihood learning. Now, we could very well decide to use some of the techniques from the energy-based learning or the energy-based models in order to train these language models while continuing to use recurrent networks, convolutional networks, or self-attention-based networks.
And there's here a question on that we reformulate, it's more career related, and it is basically, should we be seen, should we try to be more like a specialist, let's say like the RNN expert, or try to broaden our scope and let's say do work on computer vision and also NLP and then reinforcement learning and so on?
Well, I mean, only if I knew the answer to that question, I would actually do it myself. But I don't think there is the right answer there, right? So it's more like what you think are important and interesting problems, and then you should just delve into solving those problems. One nice thing that I find, especially with the advances in AI or machine learning algorithms, is that a lot of algorithms that we use for different domains are shared. So the techniques that I use for solving problems in natural language processing are in fact the exactly same algorithms that are being used to solve problems in computer vision. And I use them to work together with system biologists on trying to predict the function of protein sequences or the structures. So what it means is that you can, as long as you ground yourself in the mathematical and theoretical side of machine learning so that you can understand and know what kind of things can be done with these new algorithms, then in fact you can choose a problem that interests you most. And then even if that problem turned out to be something that's not too interesting or fun after about a year or two, you can always move on to another problem while ensuring that the one of your fit is in this, let's say, more fundamental algorithm research.
And now the community speaks a lot about self-supervised learning. Are there any ideas or directions that you see as promising combining RNNs and self-supervised learning?
Well, in some sense, yeah. So I'm like everyone is talking about self-supervised learning, especially Yan and so on. But I'm not the biggest fan of the term self-supervised learning because I think it's a bit confusing. But okay, but in a sense that the self-supervised learning says that okay, here's an observation, but no one gave us the actual label to predict. Then we're going to create a label ourselves out of the observation. Okay, sounds good. If you think about it in that way, language modeling that we talked about yesterday is like one of the most successful and widely used self-supervised learning algorithm because we're going to take the first part of the sentence as the input and we're going to try to predict the next word, or in fact it could have been any other words in the sentence. So we've been doing self-supervised learning, especially in the natural language generation, for the many years. And then what we are seeing is that it is extremely successful. It is very important building block, perhaps the most important building block at the moment for natural language processing and natural language generation. And then I almost feel like this has inspired a lot of the other self-supervised learning algorithms and then people to work on self-supervised learning algorithms. So the answer is that do I see the promising direction in using recurrent net for the self-supervised learning? No, because the promise has already been fulfilled.
And are there any ideas in machine learning that you consider promising but that do not have yet enough attention?
Um, well, I mean, like, there's so many. But generally saying, one thing that I find really interesting is how to characterize or to categorize the problems that we solve. That is, so one interesting thing that we observe, let's say in natural language processing as well as the computer vision, is that when we train this neural network on a large amount of data, these neural networks seems to learn to capture the features that are necessary to solve problems and are most mundane and sometimes even misleading. For instance, when we train a convolutional neural network on image classification, the first thing it's going to learn is to use, for instance, simply the color or the texture to classify each image into different categories. But then often in most cases, what we want our convolutional networks to do is to look at the shape, not the texture. So we want our convolutional networks to be able to detect that the image is a cat, regardless of whether that's just a pen-based sketch or it's an actual picture of the cat. But often these convolutional networks are going to use the texture that is in the fur of the cats to tell that it's a cat. And then the weirdest thing I see is that why does that happen? Why does it actually learn to detect those mundane and often misleading statistical spurious correlations first? And then only after a long time of training, it starts capturing all those, let's say, much more interesting features. And there are, of course, interpretation from the causal inference and so on that explains us about why these classifiers, without making a strong assumptions on what are the causal, let's say, mechanism behind these classification problems and so on, that it will capture those spurious correlations, but it doesn't really tell us why these neural nets necessarily prefer those spurious correlations, and then why those spurious correlations are captured first. Is there some kind of characters or the properties of the problems that we solve that make this deep learning or the machine learning algorithms to have this behavior? Can we actually, are there a different set of problems where this kind of behavior will be reversed, for instance, or have a very different behavior in general? Then how do we actually tell whether a given problem has certain property or not? So I think a lot of interesting things boils down to, in fact, characterizing different problems into a much more fine-grained bins, and then trying to have a list of the properties that we can now use in order to guide our development algorithms as well as systems. But I don't think it may be impossible, because in a sense that the best way to characterize a problem is to solve it perfectly and then see how it was solved. But then if we could already solve the problem, well, we actually care about how to characterize the problem, right? So it's a kind of chicken or egg problem. But I think this is one interesting direction that we should think more and more about. That is to characterize the problems more carefully, and then try to come up with what is the properties of the problem that make some algorithms more appropriate, less appropriate, or give us a sense of what is a right recipe to build a good system. I don't think we are paying enough attention to this.
And well, we still have many more questions left, but not enough time. So as a last question, so can you please share with us how you got started into machine learning? What brought you to this field?
Okay, so during my undergrad years, I was on the leave of absence. I worked at some companies. I worked at a couple of startups, none of which actually was successful. So you don't know any of those companies. I don't even remember the names, though. Those are so short-lived. But when I was in my undergrad years, there weren't many courses on AI or machine learning at the department. And then only at the very final year when I came back to graduate, there were a couple of courses such as probabilistic robotics as well as introduction to machine learning opened by the new professors back then. So I took them. I thought it was interesting, but those were so different from all the other courses that I had to take from the department for my computer science degree that I my sense of what machine learning was really not there. I took the course, but I couldn't really grasp what it was. But then one day, one of my good friends was passing by the department corridor and then found one brochure, ugliest brochure ever of the master's program in Helsinki, Aalto University. It was Helsinki University of Technology still back then. And then that brochure was about the master's program in data mining and machine learning and data mining. And then I was like, wait, hold on, there's a master's program in Finland that I can apply. So I applied there and then I got admission and then I had a couple of, let's say, job offers as well, but I was like, okay, Finland is so mysterious. I just have to go there. So I went there, and then that's how I started to learn about machine learning in general. And then I took a lot of courses. The program was extremely well designed, so they were teaching us a lot of, let's say, very diverse set of topics in machine learning and data mining. And then I got really excited about machine learning, and they had a program where they assigned those new students to research labs within the department, more or less randomly, because the students didn't have say in which lab they were going to be assigned to. And then once assigned, you go to the lab once a week and then do some research and then get some stipend. And I was randomly assigned to neural net lab, which was kind of shrinking back then. So I was like one of the only few students. And I was asked on the first day to read this paper by Roland Mimisevich and Jeff Hinton on using Boltzmann machine to automatically learn the style of an image. I mean, these days, style transfer is so fancy, but if you look for the root of the style transfer, that goes back to like 2009, where they had a higher order deep Boltzmann machine that can learn to transfer the texture or something like that. I was reading the paper. I could not get a single idea out of it. I couldn't understand the equation. I couldn't understand the intuition. So I started to read the David McKay's information theory book because it actually has a chapter on the Boltzmann machines. And then I was fascinated by the whole idea behind the neural network back then. So that's how I started work on machine learning. So I got into machine learning relatively late in a sense that these days I get the applications for PhD program and master's program, and then somehow everyone has been looking into this machine learning and AI since their high school years. I don't think that's necessary. It's not a field that requires you to spend too much time already in high school. But yeah, that's how I got into this machine learning. So only when I entered my grad school.
Well, it's a very entertaining and interesting story of your background. And well, we have now covered so many things on NLP, but also neural networks and the whole field in general. So, Kay, thank you very much for the time. It has been very insightful and entertaining. And
Thank
also, some comments are that your slides are really nice, so
you.
people can really get some knowledge out of them.
Okay.
And thank you very much for the time spent.
Well, thanks for the invitation. It was a great summer school. It's so sad that I couldn't be there in person, but hopefully in the future I'll be able to stop by in person and then meet all of you.
That's what we intend.
Sounds good. I'm totally on board.
Great.
All right.
Well,
Then see you
then have
later
a nice
then.
day.
Yeah.
Bye.
Have a nice weekend. Yes.
You too.